In this video, we're going to continue our discussion of sources of magnetic fields by looking at example number 29.3. In this example, we're going to calculate the magnetic field on the axis of a circular current loop. So let's consider a circular wire loop of radius A that is located in the YZ plane and carrying a steady current I as shown in the figure below. So we want to calculate the magnetic field at an exact point P, a distance x from the center of the loop. So this is the setup of my problem right here. So we have a loop. So this loop is sitting in the YZ plane. And we want to calculate the magnetic field at a point P that is at a distance x from the center of the loop. So again, I can set up my system right here. This is my ds vector. This is my r hat vector. So notice that there is a 90 degrees between my ds vector and my r hat vector. And in this example also, my current is going in the counterclockwise direction. So I can set up my my integrals like this. So again, if you notice that the cross product of ds and r hat is just given by the magnitude of ds, and the reason is because in this example right here, my ds is at 90 degrees with respect to my r hat vector, and my r square is just the distance from this point to this point, which is just again, you can see that r square is just a square plus x square. So now by symmetry, when I calculate the magnetic field, I only need to focus on the component that is pointing in the x direction. So as you can see, I can write my magnetic field vector. I can break it into two parts. So there is one component that is pointing in the x direction and one component that is pointing at 90 degrees with respect to the x direction. So by symmetry, when I do my integrals here, I only need to focus on the contributions that is coming from the x component. So I can say that the magnetic field pointing in the x direction is given by this. Again, I can calculate my cosine of theta using this equation right here. And so by substitution, I can write my bx is given by this integral. So when I do this integral here, because I'm only doing integral with respect to dx, it means that the a squared plus x squared, all of these are just constants. So it means that I can write this equation as mu naught I over 4 pi, and then you have a divided by a squared plus x squared raised to the power 3 over 2 times the integral over ds. Now the integral over ds is simply given by 2 pi times a, which is just the total length, is the circumference of this circular loop. So this is just 2 pi times a. So if I substitute this, I end up with this final equation right here. So this is my bx value. So my magnetic field, again pointing in the x direction, is given by this equation. So this makes a lot of sense because if you look at this setup right here, you can see that the current is pointing in the counterclockwise direction, and so by the right-hand rule, we notice that the magnetic field is going to be pointing in the x direction because the current is flowing in the counterclockwise direction. So again, the right-hand rule tells me that when I calculate the magnetic field, I only need to focus on the component that is pointing in the x direction. All right. So now we can calculate the magnetic field at the center of the circular loop. So if you want to calculate the magnetic field at the center of the loop, again, if you just go back to this equation right here and you substitute x equals to 0. So if you want to calculate the magnetic field at the center right here, where at this point x is equals to 0. So if you plug in x equals to 0 here, you obtain this value. So this is the magnitude of the magnetic field at the center. So again, we know that the current is flowing in the counterclockwise direction. So because the current is flowing in the counterclockwise direction, you can see that the magnetic field at the center is just pointing up. So because the magnetic field is pointing up using the right-hand rule, so again, if current is going in the counterclockwise direction, then the right hand rule tells me that I have a magnetic field that is pointing up. So if the magnetic field is pointing up, it means that this is my north and this is my south. So you have magnetic field lines going from north and always pointing from north to south. So it means that a loop of wire is almost like a magnet. It's like a bar magnet. So this is the north and this is the south. And so when the wire carries a current, it generates a magnetic field that is almost like the magnetic field of a bar magnet. All right. Now, what if I'm interested in calculating the magnetic field at a point on the x-axis that is very, very far away from the loop? So again, I can do this by looking at, so if you want to calculate a magnetic field at a point that is very far away from the loop, it tells me that the distance x has to be way, way larger than the radius of the loop. So again, when x is way larger than the radius of the loop, then all of this equation here is just going to simplify to this expression right here. So notice that I can also rewrite this equation here as this. So again, the mu here is just the magnetic moment. So this quantity here is just the magnetic moment. So the magnetic moment is just the current times the area. So it's A is I times pi radius square. So mu is equals to I times pi radius square. So if you just rearrange this equation here, you can write it in this form where mu is equals to I times the area, which is I times pi radius square. All right. So we said that the Earth is also a source of magnetic field. So the Earth is considered like a giant magnet. So you have the magnetic north and the magnetic south, and you can see that the magnetic field lines always point from the north to the south. So going from here to here. So the Earth itself is acting as a bar magnet, and so the Earth does produce a magnetic field. It's a very weak magnetic field. It's about 10 to the negative 5 Tesla. So the Earth produces a magnetic field. It's a very weak magnetic field, but it's acting as a bar magnet. All right. So now, in this example, what we're going to do is that we want to calculate so we want to look at the magnetic force between two parallel conductors. So this is a picture right here. So suppose that we have two conductors. So this is my first conductor right here. It carries a current I1, and this is my second conductor. It carries a current I2, and we know that the distance between the two is A, and so each of these has a length L. So again, we're going to assume that these are very, very long conductors. So I want to calculate, for example, what is the magnetic force F1 produced on this conductor here. So the point is that since conductor number 2 carries a current, it's going to generate a magnetic field B2, and this magnetic field B2 is going to exert a force on the conductor in conductor number 1. So I can calculate the force using this equation. So I know that F1, so the vector F1 is just I1 times L, the length vector cross B2. Or if I can calculate this in terms of the magnitude, I can say that F1 is just equals to I1 times L times B2. And again, remember that B2, so by the right-hand rule, the magnetic field produced by the conductor number 2 is always going to be pointing. At this point, it should be coming out of the board, so it's pointing out of the paper. And so when you take the cross product of B2, and because L is pointing in this direction right here, so L cross B2, there is a 90 degrees angle here. So in terms of the magnitude, F1 is just given by I1 times L times B2. So I know that B2, I can substitute B2 by mu naught I2 over 2 pi times A, because we know that the magnetic field B2 produced by a very long conductor is just given by this equation right here. So if you substitute that, you can calculate your F1 using this equation here. So generally, sometimes we calculate the magnetic force per unit length, and so if you take this value and you just divide by the length, it's given by mu naught I1 I2 over 2 pi A times the radius times the distance between the two. So again, notice in this equation that so what is interesting here is that whenever you have two conductors that carry a current in the same direction, then you get a force of attraction. So the force here is going to be an attractive force. So if two conductors carry current in the same direction, they experience an attractive force. And if they carry current in an opposite direction, then you have a repulsive force. All right. So again, we can go into this equation right here and calculate. So if you go here and just plug in the values, then we can calculate, for example, when the magnitude of the force per unit length between the two long parallel wires that carry identical currents and are separated by 1 meters is 2 times 10 to the negative 7 Newton per meter, then the current in each wire is defined to be 1 amp. So we can use this as the definition of the amps. Okay, so I'm going to skip this quiz here. This is quick quiz number 29.2. I'll let you guys take a look at that. All right, so the final example in this video is example number 29.4, suspending a wire. And in this example right here, so what we're going to do here is that we have 3 wires. So there is 2 wires that is sitting at the bottom right here. So each of the wires carry a current I2. And there is 1 wire that is at the top here that carries a current I1, and I1 is pointing in the opposite direction. So we know that the separation between these 2 wires at the bottom here is A, and I know that the current that is on the top wire is equals to I1, which is 100 amps. And we know that the wire that is at the top, has a length of L, which is equal to 10.0 meters. So what I'm going to do is that I want to calculate, so what current must the infinitely long wires carry so that the 3 forces form an equilateral triangle. So again, so what I want to do is that I want to balance the force of gravity produced by the wire that is at the top. So this picture shows everything that is going on right here. So if I look at this, if I look at the system in terms of the cross section, then you can see that I2 is going into the paper, I1 is coming out of the paper. So it means that I2 and I1 are flowing in opposite directions. So it means that the force between I2 and I1 is going to be a repulsive force, and the force between I2 and I1 here is going to be a repulsive force. So you have the force on the left wire is going to be repulsive, the force on the right wire is also going to be repulsive. So we can set up a system of equations right here. So I can calculate my force here. I can just write it in terms of the cosine, and so the magnetic force is given by that equation right here. And I know that the force of gravity acting on the top wire is given by this equation as well. And so we want the sum of all the forces to be equal to 0. So if I set that up and set that equals to 0 and solve, I can get my value for I2 here. And if I just plug that in, if I plug in the values, I get a value for I2 that is about 113 amps.